Hello and welcome all of you to this session of heat power engineering. In the previous session, we had discussed the concepts of Gardner cycle. We have also seen that there are four specific ideal processes which are involved in a Gardner cycle. But we have also discussed that Gardner cycle is not used practically because there is a huge pressure ratio which exists during the expansion process, and such pressure generation is quite impossible in the practical scenario. So, for different purposes, you know that for different automotive engines, there are several thermodynamic cycles which are involved in it. So, one of the most important thermodynamic cycle is the Otto cycle, which is generally used in the cases of petrol engine. So all of you have studied the concepts of petrol engine, and therefore you know what what are the different processes that are involved in the petrol engine. So Otto cycle is the ideal representation of all these processes which are involved in a petrol engine. Now, so today we will be discussing the concepts of Otto cycle, the efficiency part, how do you define Otto cycle. So in case of Otto cycle, there is an important thing you must understand, which necessarily creates a difference between Otto cycle and the petrol engine, or the thermodynamic processes which are involved in Otto cycle or petrol engine. Okay, in case of Otto cycle, air is always considered as the working fluid, whereas in case of petrol engine you will find both air and fuel. That means the mixture of air and fuel, they are the working fluid there. And in case of Otto cycle, you will understand the necessary heat generation, the thermal energy generation, or the necessary combustion process, the heat transfer process which is required to generate mechanical power, that happens inside the cylinder. In case of vapor power cycles or power plants, you will find that the heat addition takes place externally, whereas in case of Otto cycle, you will understand that the heat addition part takes internally. So this is a basic difference between Otto cycle and all other vapor power cycles. Okay, that means you can also differentiate between the gas power cycles and the vapor power cycles from this aspect. So let us check the objectives which we will be going through this session. So first of all, as I have told you earlier, there will be differences in the real processes that is happening in the petrol engine and the ideal processes which are simulated to understand the characteristics of Otto cycle. So we will study these differences, and we will try to understand why these differences are present there and how it is being simulated ideally as this specific process which is mentioned in the Otto cycle. Then we will try to understand the process of combustion during the Otto cycle. We will try to understand the process of combustion during the reciprocating spark ignition IC engine. Then we will do the necessary part, the thermodynamic process calculations. We will calculate the heat transfers, the work transfers, the internal energy change for each and every process, so that we can get the value of the efficiency. We can understand the efficiency of an Otto cycle. And then we will try to relate this efficiency with the compression ratio. So being an automobile engineer, you must understand, you must know what a petrol engine is, how it is comprised, what are the thermodynamic processes, and what is the ratio which we call as compression ratio, and how does it influence the efficiency of an Otto cycle. So let's start our discussion of Otto cycle. Okay, now just have a look for the processes. You can see how the processes are running. So we will start discussing one by one what are the processes which are involved. First of all, we will start understanding these processes physically, and then we will start analyzing these processes mathematically. Okay, So let us start our discussion. Let us try to analyze these processes which are involved over here from the point of view of thermodynamics and from the point of view of physics. So before moving on to the physical processes which are involved here, we must understand the characteristics of the cylinder and the piston which is involved here. So we must understand the construction, then we can move on to the physical explanations. So first of all, you can see that there is a piston over here which reciprocates, and here you can see there are two specific valves upon which the air fuel mixture can enter or leave the closed system. Now this is considered to be a closed system where it is insulated. Ideally it is insulated, and the piston reciprocates over it. From this inlet valve, air and fuel mixture enters the system, and from this exhaust valve, the combustion products leave the system. So this is a general introduction. Then let us start with the first process. Now what happens when the piston is at uh, TDC or IDC? What happens? The inlet valve starts to open. Okay, as the inlet valve is open, what happens? Air and fuel mixture, which is generally called as charge, so the mixture of air and fuel enters this closed system. And what happens then? Since the piston is moving in a downwards direction, you can see there is a lot of expansion uh, expansion is happening of the air fuel mixture. Since the piston is moving in a downwards direction, so obviously this air fuel mixture is getting opportunity to expand itself. So due to this sudden expansion, what happens? The pressure at which this air and fuel was introduced into the cylinder, the pressure of this air fuel mixture drops below the atmospheric pressure. Generally it is considered that air fuel mixture enters into this cylinder at 1 atmosphere pressure. Now since this piston is moving downwards from TDC to BDC, then what happens? This this air fuel mixture tends to expand itself. So that means the pressure goes below the atmospheric pressure, so the suction is being created and more air fuel mixture is being taken into the system. Now what is this IDC and what is this TDC? So IDC is the inner dead center and TDC is the top dead center. ODC is outer dead center, BDC is bottom dead center. So these are the points by which you can understand, you can limit the maximum possible expansion and the compression of a cylinder. Okay, so this piston moves between TDC and BDC. IDC and ODC are generally used for, it can be used for all possible engines, whereas TDC and BDC, the concept of TDC and BDC can only be used for vertical engines. Okay, so the piston moves between the IDC and ODC. Now the volume between IDC and ODC or TDC and BDC is called as the stroke. So one stroke means it is the volume, it is the displaced volume between TDC and BDC or IDC or ODC. Okay, so when the piston, so let us start from the beginning once again. So when the piston is at IDC, what happens? This valve opens, fresh air and fuel mixture uh, is taken into the system, and the piston is starting to move downwards. Then what happens? Suddenly the air fuel mixture was taken into the system in 1 atmospheric pressure. Now what happens then? Suddenly, due to the expansion of this air fuel mixture, the pressure falls below the atmospheric pressure, and a suction is being created so that more and more air can be taken into the system. Now, thermodynamically, this process is considered as a uh, constant pressure process. Okay, ideally, in case of Otto cycle, it is considered as a constant pressure process. But practically, this process diagram would be little different. So let us show you how the real process deviates from the ideal one. So let us see that. So here you can see this is a constant pressure process, which is the ideal, and it is the assumption which is taken in case of a Otto cycle. Okay, now what happens in the actual process? The You can understand that the pressure initially goes on decreasing. The pressure falls below the atmospheric pressure since it is getting chance to expand itself. So obviously the pressure drops. And but what happens when the air fuel mixture, the mass of the air fuel mixture goes on increasing, the pressure once again increases. So this dotted line, this curve indicates the change in pressure during the suction stroke. So this is our first stroke, which we call as suction. Now what will happen? Now the piston is at this position. Okay, the piston is at ODC or BDC, and this cylinder is full of air fuel mixture. The cylinder is completely filled up with air fuel mixture. Now what will happen? The piston will start moving in this direction, in the upwards direction. Then what will happen? It will start compressing the air fuel mixture. It is very simple as that. Now when the piston starts to move in the upward direction towards TDC, compressing the air fuel mixture, what will happen? The pressure and the temperature would rise. The pressure and the temperature of the air fuel mixture would obviously rise. But you have to remember that this temperature is always less than the self ignition temperature of the air fuel mixture. So the temperature increase because of the compression by the piston is not enough to burn the fuel itself. The temperature raised is always less than the self ignition temperature. So to, to burn the fuel, to create the enormous energy which we need, and by virtue of this enormous energy we are going to get the mechanical power. So this process happens by the help of an igniter. So an igniter ignites this air fuel mixture, which is already at a high pressure and high temperature. Now what happens? Generally, in many books or loosely, it is said that high heat is being generated or high heat is being liberated. Now always remember, heat is the energy which flows. Heat is an energy in transit. It is an energy in transit. That means it can only flow when there is a certain temperature difference between the system and the surroundings, or vice versa. Now the question is, heat cannot be generated. That's as simple as it is. So what happens? So the fuels contain chemical energy with them. So it is a kind of internal energy which gets liberated because of the chemical reaction which is happening between the fuel and air. Okay, so it is a exothermic reaction. It is a exothermic oxidation reaction. Okay, so and it is very fast. So it is, you can add a word, rapid exothermic oxidation reaction. So because of this rapid exothermic oxidation reaction, what will happen? High thermal energy will be generated. Okay, so high thermal energy would be generated. Now what will happen? The piston is at now ITC. Okay, the piston has compressed the air fuel mixture, and the igniter has provided the necessary ignition to it. So the chemical reaction has started. The energy the thermal energy is being generated now, and the piston is at IDC. Okay, then what will happen? This process is considered to be very fast, very rapid, or instantaneous. So this fuel burning process and the generation of high thermal energy is considered to be a very rapid and instantaneous process. So when the piston is at TDC, this rapid exothermic reaction takes place, and you understand we can generate the mechanical power by the virtue of this exothermic reaction, and then the piston again start to move in the downward direction. Okay, but the combustion is taking place at 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 when the piston is at TDC. So we consider this process as a constant volume process because it is so instantaneous. The piston doesn't have any time to go downwards. Within that very small time, the burning of the fuel is happening. Okay, so this is considered as a constant volume process. So this is the combustion characteristics of the petrol engine. So before combustion, what is happening? The compression is happening, right? Which we haven't mentioned. Actually, we have discussed it, but we haven't drawn the thermodynamical process diagram. So before combustion, what happens? Compression happens. Okay. So before combustion, compression is happening. Now, what kind of thermodynamic process is this compression? So it is considered ideally as an isentropic compression. That means since it is a closed system, and in this closed system it is also insulated so that no heat transfer happens in with the surroundings, we consider that it is an reversible adiabatic process. But it is easy to identify practically a process cannot be reversible, so there will be obviously some frictional losses and anything. Okay, and everything is happening which makes the process irreversible. So the assumption of irreversible adiabatic process is an ideal one. Okay, so ideally how we can draw this process? We can draw this process by this diagram. Okay, so we can ideally draw this process by this diagram. I would like to draw it once again so that it can be seen in a beautiful way. Okay, so this is your compression process. This is the ideal compression process. That means it is isentropic compression. And then what happens? The combustion happens, and we have already mentioned that the combustion is so instantaneous the piston doesn't have any time to move downwards. So we consider this process as an constant volume process. So from 1 to 2 it is an isentropic compression, whereas from 2 to 3 it is an isochoric or constant volume heat addition process. Okay, constant volume thermal energy generation process where the combustion is taking place. So before suction, after suction compression, what is happening? We call it as power stroke. Okay, so power stroke means it is the combination of the combustion plus the mechanical power generation. So when the combustion is happening, the after the combustion has occurred, the piston will again move in the downwards direction, from TDC to BDC. Okay, so it will move in the downwards direction, and this exhaust valve will be open, and the products of the combustion will be removed from the closed cylinder. And when the piston is in its downwards motion, the fresh air will start to enter this closed system. And when the piston will again move in the upwards direction after it has reached BDC, and when it is moving from BDC to TDC, it will push the products of the combustion which is already remaining in this cylinder, it will push the combustion products outside of the cylinder, and it will intake the fresh air fuel mixture will be taken into the system, so that this cycle repeats. So this power stroke is a combination of the combustion as well as the expansion. Okay, so we can draw like this, and again the exhaust is taking place, and again the exhaust is taking place. Okay, so you can write draw like this. So this is the exhaust process, so you can draw right 3 over here and this 4. Okay, so for from 3 to 4 it is considered as an isentropic expansion, which is exactly opposite to the isentropic compression. Okay, so now the question is, what happens really when this combustion takes place? So ideally it has been considered as an insulated surface which doesn't transfer heat, but the temperature, the amount of thermal energy generation and the temperature at which is raised at this within this cylinder, that is at this is very high. The cylinder materials are not so much strong to withstand those high temperatures. So what is happening in the practical case? Along the lateral surfaces of this cylinder, a cooling system is always provided, so that heat transfer can occur between this water flowing outside of the cylinders and the thermal energy which has been generated within the cylinder, so that the longevity of the material can be kept intact. Okay, so this is the diagram, this is the indicator diagram. Here you can understand the 4 fundamental processes which are involved in a reciprocating spark ignition engine. Now we shall move on to the description of the thermodynamic processes which are involved. So this is called as an indicator diagram. Okay, now we will move on to the thermodynamic diagram. Okay, so before that I would like to show you the animation once again. So here you can see, this is the intake, this is the compression, this is the combustion, and here goes the exhaust. So this blue or the sky blue is the intake, this red is the combustion, compression and combustion, and this gray ash is the exhaust. So now I believe you can understand these 4 separate processes which are involved over here. Okay, so with this let us move on to understand the PV and TS diagram. Okay, so we have already discussed the PV diagram. Now for the thermodynamic diagram, we neglect the exhaust and the suction part. We only deal with the 4 fundamental processes which are involved in an Otto cycle. Okay, so this is a PV diagram for you, and you know this has been considered as a constant entropy process. It is a reversible adiabatic process, so the entropy remains constant. So this is why this is a straight line in the TS plane. Okay, then what happens? Constant volume heat addition, isochoric heat addition takes place. So here heat is being added, and again the reversible adiabatic expansion takes place. Okay, so this is the reversible adiabatic expansion. That means isentropic expansion. That means entropy remains constant. So this is a straight line over here, and then constant volume heat rejection once again. So these are the basic explanation of the PV diagram and the TS diagram which are involved in a Otto cycle. We shall now introspect the processes, the thermodynamic aspect of it, and we will see how mathematically the various process variables can be calculated for Otto cycle. So let us do that. So in the previous class, while discussing about Carnot cycle, I have told you that the change of internal energy the change of internal energy is always given by this formula, CV into delta T. That means CV, that means specific heat at constant volume, into the change of temperature. So if you consider the process 1 to 2, so it will be CV. So what is the temperature change in this process? From 1 to 2. So you can write T2 minus T1. So we will first do the internal energy change for all these 4 processes. Okay. Now for 2 to 3, it will be simple. It will be simple. The same old rule will be followed. T3 minus T2. Okay. T3 minus T2. Now if you analyze the signs, if you analyze the temperatures, then you will understand what will be the signs of this internal energy change. Okay. So CV T4 minus T3. So CV into T4 minus T3. Very simple thing. And it will be CV into T1 minus T4. T1 minus T4. Okay. So if you, okay, we will do it later on. Now the question is, we know this is our fundamental equation, the first law of thermodynamics. dq is equal to du or delta u. Better to write delta u so that no confusion can be arise. Okay, so and it is dw. So this is the first law of thermodynamics. Now if you apply the first law of thermodynamics for process 1, the process 1 to 2 is an isentropic process. That means it is an adiabatic process which is happening in a reversible way. So for adiabatic process, this there is no heat transfer involved. So you can simply write 0 over here. Now if this becomes 0, so that means dw would be minus of delta u. Very simple. So you can write Cv into T1 minus T2. Cv into T1 minus T2. Very easy to write. Okay, now let us move on to the next process, process 2 to 3, where heat is being added at constant volume, or thermal energy generation is taking place because of the rapid exothermic chemical reaction. Okay, so since it is a constant volume process, and you know the displacement work is given by this formula PdV. Since there is no change in volume, that means this dV would become 0. This dV would become 0. That means for process 2 to 3, the work done will be simply 0. And if this becomes 0, then heat transfer would be equal to the change in internal energy. This is as easy as it is. So you can write Cv into T3 minus T2. Very simple thing. Now again, for process 3 to 4, it is an adiabatic process, so there will be no heat transfer. And if this is 0, so the dw becomes minus of delta u, so it can be written as Cv T3 minus T4. Now I would request you to go on analyzing the signs. Okay, analyzing the temperature so that you can understand what are the signs involved in it. If it is positive, if heat transfer is positive, that means system is gaining heat. And if work is positive, that means system is doing work on the surroundings. If it is negative, then the opposite happens. So you know those things, but a little bit of recapitulation for you. So again, for the process 3 to 4, it is a constant volume process. So the PdV work is 0. You can write 0 over here. And if this becomes 0, then delta Q, dq is equal to delta U. So you can write Cv into T1 minus T4. Okay. So to validate the first law of thermodynamics, you can check. How you can check? You know, for the first law of thermodynamics, to validate the first law of thermodynamics, the internal energy change for all the 4 processes for this cycle, it will be simply 0. And you can do it by yourself, you can check it by yourself, and you will see that the change of internal energy would be simply 0. And another one important thing is that the all heat transfers, the sum of all heat transfers would be equal to sum of all work transfers. Even you can check this and you will find the same thing. So with this, we will now move on to the discussions of efficiency. How do we calculate efficiency for Otto cycle? So let us check that. Okay, so for any heat engine, the efficiency is defined by 1 minus heat rejected by the heat addition. So for this Otto cycle, the heat addition, if you write heat addition as QH, so it will be CV into T3 minus T2. Okay, it will be CV into T3 minus T2, as you can see over here. Now the heat rejected is, so if you are considering that heat rejected, that means it is already in the negative sign. Okay, so if you write CV into T1 minus T4, so if you write this, what will happen? It is mathematically negative. Okay, so it is mathematically negative, and you are writing the term heat rejected. So you have to write, if you are considered with heat rejected, so you should write T4 minus T1. Okay, so this is the simplistic assumption one must understand to pursue the derivation of the efficiency for Otto cycle. So it will be QC divided by QH. That means CV into T4 minus T1 divided by CV into T3 minus T2. So this CV terms will not exist in the equation, and ultimately you will get the efficiency as T4 minus T1 divided by T3 minus T2. Now you can understand that the efficiency which we have written over here involves all the 4 possible temperatures. So our motivation will be to simplify this efficiency term. Our motivation would be to express the efficiency in least possible terminologies so that it becomes simple to understand, simple to explain, okay, simple to analyze, because the number of variables as you go on reducing, it becomes so simplistic. Okay, so this is a very common thing you must understand. So with this, now let us move on to the analysis of efficiency, but you must remember this term. Okay, we'll see just in a moment. So let us start our calculation for efficiency. So for these two processes, you can see that for this process 1 to 2 and process 3 to 4, it is an adiabatic process. So the expression PV to the power gamma equal to constant will follow, and we have already seen while discussing the concepts of Carnot cycle, if you consider air as an ideal gas, and if you replace this P by RT by V, then this equation, this relationship between temperature and volume, can be created for any adiabatic process. Okay, when air is the working fluid. Now if you apply this process, this relationship for process 1 to 2 and 3 to 4, we can see a certain relationship between temperature and volumes. Before that, we would like to mention a certain parameter by which the efficiency of Otto cycle is described. Since any automobile engine is designed on the basis of maximum and minimum volume of the cylinders. Okay, since any automobile engine is always designed on the maximum and minimum possible volume, so it is quite understand the relationship between maximum and minimum volume which a cylinder can possess should be an important parameter. So the ratio between the maximum volume and the minimum volume is defined as the compression ratio. As you know, from the practical perspective, from the perspective of an engineer, your space is predefined, your space is fixed. So it means that your maximum volume and minimum volume should also be predetermined. So the ratio between the maximum volume possible and the minimum possible volume is defined as compression ratio. So this compression ratio RV is equal to max volume divided by mean volume. Okay, now max volume divided by mean volume. Okay, max, I'd like to correct it because it seems odd. So it is max volume divided by mean volume. So it is max volume divided by mean volume, or sometimes it is also written as volume before compression. So before compression volume before compression, that means from the thermodynamic diagram this is your volume, and you can see that this is the maximum possible volume which is possible. So volume before compression. Okay, so volume before compression. So you can see that the compression ratio is the ratio between volume before compression, that is V1, and volume after compression, that is V2. Since 2 to 3 is an isochoric process or a constant volume process, constant volume heat addition process, you can write V2 equal to V3. So I have replaced V2 by V3 and V1 by V4, since this is also a constant volume heat rejection process. So V1 is equal to V4. So that has been written over here. So this compression ratio can be defined as V1 by V2, or you can write V4 by V3. Now what we will do is we will see what is the temperature volume relationship for these two processes. So you can write T1 into V1 to the power gamma minus 1 is equal to T2 into V2 to the power gamma minus 1. So when you are applying this fundamental law for this process, that means you can simply rearrange this equation in such a way you can write, so I'll do it in this way, T2 by T1 is equal to V1 by V2 to the power gamma minus 1. Okay, I am trying to express this formula in terms of RB. That is why I rearranged this equation in terms of this. Okay, so gamma minus 1, that is equal to RV to the power gamma minus 1. Again, if we express this relationship for the process 3 to 4, what will happen? You can write, I'm not writing the fundamental equation, I will directly write it. So here you can see that it will be something like this, V4 by V3 to the power gamma minus 1. So obviously it will be T3 divided by T4, because this is your relation. So here you can write T3 by T4. So here you can write T3 by T4. Now this is also the compression ratio to the power gamma minus 1. It can be easily understood. So now you can write T2 by T1 is equal to T3 by T4. Very easy to understand now. T2 by T1 is equal to T3 by T4. Very simple. Okay. T2 by T1 is equal to T3 by T4. Now if we do a little bit of rearrangement, if we take this 4 here, if we take this 4 here and this 2 here, then what will happen? You can see this equation, T4 by T1 is equal to T3 by T2. Now what I will do, I will subtract 1 from both the equations. So minus 1 is equal to T3 by T2 minus 1. Okay. So that means it will give you this form, T4 minus T1 divided by T3 minus T2 would be it would be simply T4 by T1. It would be, okay, just let me do this thing. It will be T1 by T2. Okay, so it will be T1 by T2. Now I will just clear everything over here. Just I will keep this relation. We have seen that okay, so this efficiency of Otto cycle can be written as 1 minus T1 by T2. So T1 being the temperature before compression and T2 being the temperature after the compression has taken place. So in terms of compression ratio, this can be also written in a little bit of different way, where you will find that this compression ratio only affects the efficiency of the Otto cycle, or in other words, the efficiency of Otto cycle is dependent only on compression ratio. So T2 by T1 is equal to RV to the power gamma minus 1. Then it will be simply this gamma minus 1. So 1 minus 1 by compression ratio to the power gamma minus 1. So now it is easily understood that if the compression ratio goes on increasing, then the efficiency of Otto cycle would also go on increasing. This is as simple as it is. Okay, so now you can see these are the two terms. These are the efficiencies of Otto cycle in terms of the temperature related with the compression, temperature before compression divided by temperature after compression, and this is the efficiency of Otto cycle in terms of compression ratio. Okay, so you must remember these two formulas, this two arrangement, because this is a very simple thing to arrangement, very simple thing to remember, and it will also help you while solving the mathematical problems. Okay, so with this and with this understanding, if you go on increasing the compression ratio, the efficiency of Otto cycle would also go on increasing. Okay, so this is a very simple thing to understand. Now let us move on to see the effect of the influence of high compression ratios or the increase of compression ratio on the change of efficiency for Otto cycle. So here you can see an important graph over here. So till this compression ratio of 8, you can see an rapid increase of the efficiency. You can see the efficiency is increasing, and then you can see this curve flattens out. That means the change in efficiency is not that much interesting or that much huge. Okay, so till 8, when the compression ratio started from 1 to 8, you can see a rapid increase or a monotonic increase in efficiency. But when the compression ratio crosses 8, it becomes flattened. That means the change of efficiency of Otto cycle is not varying with the compression ratio. So what happens actually? If you go on increasing the compression ratio, up to a certain extent, the temperature or the pressure which is being raised, it can be greater than the self-ignition temperature. So we have already told you that there is an igniter present in this. Okay, the air fuel mixture is done at the carburetor, and from this carburetor, this air fuel mixture is entering the system. So uh, if you go on using high compression ratio, so that the temperature and the pressure which is raised up to a certain extent, so that it becomes higher than the, I'm sorry that I have written igniter over here. So if it becomes higher than the self ignition temperature, then a premature burning can cause. Okay, this phenomena is called as auto ignition. Okay, so because of this premature or incomplete burning or incomplete uh, combustion, what happens? An audible sound is being produced, and this audible sound or this phenomena is called as knocking or detonation. Okay, so to solve the problem of knocking or detonation, we use anti-knocking agents. Generally, tetraethylate was used as an anti-knocking agent, but due to the pollutive effect of lead, present days, this tetraethylate is not used. Okay, so this is the phenomena of self ignition, or sorry, auto ignition, and the phenomena of knocking. And for gasoline engines, here you can see the typical compression ratio is 8 to 10. Okay, where an anti-knocking agent is being used. Okay, so with this, let us now see what we mean by mean effective pressure. Okay, so before that, I would like to write a formula so that it becomes easier to understand. So this is the general formula of displacement work or the PDD work, which I have told you so many times. Now, in case of Otto cycle, if we consider a constant pressure which is acting over the entire power stroke, which is exactly constant, and it is working over the entire power stroke, and this fictitious pressure, this hypothetical pressure, is doing exactly the same amount of work which the engine is performing. Okay, then this pressure is called as the mean effective pressure. So this is a fictitious pressure, and the importance of uh, uh, this concept is that you can analyze the engines from this. You can analyze the performance of engines from this parameter, from the help of this parameter. Okay, so mean effective pressure is nothing but the net work done by the engine, divided by the volume which is being displaced. So divided by the volume which is being displaced. Okay, so this is your mean effective pressure. So for any engine, you can derive the mean effective pressure, and this mean effective pressure would give you the characteristics of the engine on terms of from the terms of developing work, or you can say from the terms of efficiency. So using the parameter mean effective pressure, you can uh, characterize the efficiency of different engines. Okay, so with this, we would complete our discussion today here. In the next session, we will start discussing about the diesel cycles. So till then, goodbye and thank you.